So, hi everybody. It's my pleasure to introduce Junu Jeong. He's our collaborator on the alpha experiment he's at Stockholm University. He started July 1st. Before that, he was in South Korea on the CAP experiments at HEIST. He'll tell us about exploring Axions plans at Stockholm.
Thank you very much for the introductions. Yes, my name is Junu Jeong from Stockholm University, and yeah, I'm very glad to present this research topic in front of you. And thanks very much for inviting me to give an opportunity to present this thing. So let me start. So today I'm going to talk about the high-mass interaction searches and also plans at Stockholm University. So yeah. So this is the outline of my talk. First, I will introduce Axions, even many of you already know about that. And then I will move on to the haloscopes, especially focusing on the Resonator developments, and then just explain about our plans at the Stockholm University. And I'm pretty sure that I have no time to cover the last section, other high-mass section searches, but let me see if I have time or not. If I don't have time, then I just skip this section and go to the summary. So let me start from the Axions. So let's think about the neutrons. Neutron is a composition of the UDD, a very well-known elementary particle, and it has a net charge of the 0, and it is spin 1/2 state of these compositions and having a non-zero dipole moment. And the question is whether this neutron can have an electric dipole moment or not. But because this is a spin 1/2 particle, 1/2 elementary particle, the only direction that this particle can have is the spin direction. So if this neutron have an electric dipole moment, then the direction for the EDM also should be parallel to the spin direction. And the problem is that the coupling between the electric field with the electric dipole moment is actually CP odd in terms of the Hamiltonian, and this breaks the symmetry of this system. And actually, in quantum chromodynamics, QCD predicts the existence of these CP breakings from this Lagrange density called zeta term, and here small g is the gluon coupling constant, large g is the gluon field strength tensor, and zeta y is the degree of the CP violations. And it is some of the two very independent sources. One is coming from the gluon's vacuum state, and the other one is coming from the mass angle of the quark mass matrix, which is given by Higgs mechanism. So, and each of those two are expected to be order of 1, so the sum is also expected to be order of 1. So people try to measure the strength of the EDM, but up to the order of zeta, for the zeta order of 10 to the minus 10, people couldn't find any evidence. And this becomes one of the most famous fine-tuning problem, or strong CP problem. Why is this should be such small? Was there any questions? No. So to resolve this problem, Pechai and Kin bring a very clever idea for Pechai-Kin mechanisms. So what they notice is that actually this CP violating Lagrange density actually have a minimum energy when zeta bar is 0. So what they propose is they promote the zeta bar from constant to the dynamic field. Then as the universe expands, zeta bar naturally goes down to the 0, which is the vacuum state. So it's resolved the strong CP problem. And the action is just a small oscillation of the zeta bar around 0. So this action is kind of a clue of the Pechai-Kin mechanisms, just like Higgs is a clue for the Higgs mechanism. And if this kind of promotion from constant to the dynamic field, of course, at a very efficient high energy scale, then this the action can very deeply interact with the other standard model particles. And also, because of this rolling down mechanism, which is called the misalignment mechanism, it is expected to have a sufficient amount in the universe, in the non-relativistic states. And these two characteristics were aligned with the characteristics for the dark matter. So this is the reason why axion is a strong candidate for the dark matter. So I will recap on why axion is important. Axion has a very strong theoretical background from the strong CP problem, and also it is a very strong candidate for the dark matter. And many the beyond standard model actually adopt these actions, and it's kind of ubiquitous in the theory as well. And in terms of the theory experimental side, the search method is actually very well aligned with the rapidly growing quantum technology recently, which is also one objective point for the axions. And relatively smaller scale of the type experiment also can take this action, which is also one of the objective points. And there has been a lot of global effort to search for documentary action, and this class shows one of these efforts in the as exclusion limits. So the y-axis here is the action photon couplings, and the x-axis is the action mass. And the central yellow band corresponds to the theoretically prepared region for the QCD actions, including the two representative model, KSVG and DFSC. And other colored regions corresponds to the experimentally excluded regions, including the hashtag NPA and also CADPA and other experiments has been conducted very actively so far. So here I have been covered a brief introduction about the action, and now I will talk about the high-mass cavity telescopes, focusing on the cavity development. So to do that, let me just recap on the methodology for the cavity telescope. So it has been actually proposed by PLSKD about 40 years ago, and still we are using this methodology. So the key idea is that you can first we prepare a strong solenoid magnet which can apply a magnetic field in a localized region like this. Then thanks to the axion photon coupling, this magnetic field with the interaction of with the documentary action can induce vacuum current density with this kind of form. Here J gamma gamma is the axion photon coupling, and gradient A is the action's wind. But we usually assume the action is cold, so we neglect this term. Also, we don't apply any electric field inside, so this first term can be neglected, and then the induced current density becomes parallel to the applied magnetic field and oscillates with the action's frequency. And we can put a microwave cavity inside this solenoid, and once the cavity frequency matches the action frequency, documentary action frequency, then documentary action can resonantly convert into photons inside the cavity, and this photon can be read out through the additional electronics like this. And the expected command power is given with this kind of form. Here, these grays correspond to the theoretical parameters, action photon couplings, documentary action density, action mass, and the others are experiment parameters applied by field, cavity volume, Pareto vector, and this one is the for the form vector, which describes how well the electric field of the ball inside the cavity align with the applied magnetic field. And this is given with this kind of form and is defined between 0 and 1. And usual cavity telescope experiment has a form vector of about 0.5 or 0.6 and even 0.7 depending on its geometry. And also because we don't know axion mass a priori, we have to insert additional tuning system inside the cavity. So we should tune the cavity frequency to search the possible documentary action's mass. So therefore, the most important parameter for this haloscope experiment is for the scanning rate, which represents how fast we can scan the given action parameter space, and it has this kind of proportionality to the relevant parameters. So basically, we are doing work to maximize this scanning rate. One way is using a very strong magnet, large volume of the cavity, increasing Pareto vector, or lowering system use temperature. So let me go back to these exclusion limits. So as you can see, you could naively see that there is a quite empty space in the high-mass regions, and there is one reason for that. This is kind of one characteristics for the cavity haloscope. So if we want to go higher frequency regions, then we actually should reduce the size of the cavity because the resonant frequency of the cavity inversely proportional to the size of the cavity. So because of that, we lose a lot of the volume, and therefore the scanning rate decreases a lot proportional to the target frequency in terms of minus 20 over third power to the target frequency. So if we increase the target frequency twice, then we lose the scanning rate vector of 100, so which is very critical. So that's the reason why the higher frequency regions are quite empty currently. However, several theoretical attempts to predict the mass for the documentary action has been proceeded, and many different theory groups have tried to predict the documentary actions mass, but it turns out that even independent theory group prefer to and suggest to have a higher mass regions for the dark matter action. So because this is just a cosmological simulation, it does not actually give the exact answer, of course, but as a kind of experimentalist, we get kind of forced to go higher mass regions, and it's a kind of strong motivation to search for high mass dark matter actions. And as Dana introduced me, so I was in the CPP previously, and I have been actively developed the volume efficient way to search for high mass dark matter actions, and this designs are kind of summary for the design that I have been conducted at CPP. So I will just explain a bit more detail about its designs. So the first cavity design is a multi-cell cavity. So instead of having this kind of smaller size of cavity, we have proposed to inserting this kind of metallic partition inside the cylindrical cavity. And one breakthrough is that we made a certain central gap at the center, which makes this circular sector cavity connected, and therefore forming a single cavity. So we only using a single antenna, we can extract all the converted power inside this cavity, and which makes the experimental setup much robust and simpler. And also because we are only adding this smaller metal partitions, so the volume loss is very small, and also by adjusting the size of the central gap, we can make this design can be robust against mechanical tolerance errors. And also one good point is that by choosing the number of cells, we can actually select the target frequency that we want to see. And these are some fabricated cavity design for this multiple cell cavity. This is a 2-cell. If you look carefully, put never see some partition in between, and this is also 4-cell. And these holes are for the tuning rods, for the tunings of this cavity. And using this kind of cavity setup, we have connected several experiments. 2-cell experiment is in this frequency region around 3.3 gigahertz. And we also conducted 8-cell cavity experiment, which looks like this. It's highly complicated, but it gave a very good volume efficient cavity design for 6 gigahertz regions. So we could reach down to the near case with sensitivity. Also, we have used the recently 3-cell cavity experiment at 5 gigahertz regions. And the next thing we have considered was using a higher order mode. So like a TM030 mode of the cylinder cavity. So instead of using smaller size, again, we are considering using a higher order mode. And this green curve actually showing the electric field profile for the higher order mode in the radius. So, but the problem of this higher order mode is actually one of the problem is it has some relatively oscillating region in terms of the field strength, so which actually degrade the form factor. But however, if we place a direct tube in the very proper region between at the certain at the proper position of the cylinder like this, then all this opposite sign electric field can be concentrated into this directed region. Therefore, the form factor can be recovered up to 0.4 or 0.3 to 0.4. So therefore, which is not that bad form factor, so we can still use this design. And it also the benefit is we can also have a high quality factor, and of course no volume loss. And already this single cavity, so single antenna is enough to detect the signal. But the problem was what is the tuning method for this? And there were several tuning methods that, but one tuning method we have proposed was the peer tuning method, which is splitting this directed tube into 2 segmented layers like this. Then by rotating the inner layer against the outer layer, then we can effectively change the thickness of this directed tube. Then this region can be changed to something like this. Then therefore we could change the resonant frequency of this cavity. And we have made this kind of prototype cavity for this design. So this corresponds to the outer dielectric segment, and this is the inner layer. And by rotating the inner layer, we could successfully tune the frequency that we desired. Is correspond to this one. Yeah. And the next thing we recently did is going more higher order mode, which is photonic crystal cavity actually. So we consider implementing the array of the dielectric rods, something like this. So if each circle, black circle in this cavity corresponds to the dielectric rod, and if we position those dielectric rods properly, then all the negatively oscillating region can be concentrated inside this dielectric as previous higher order mode cavity. So the form factor can be also recovered up to 0.3 to 0.4. So form factor is not bad. Also the five factor for this cavity mode is very good. And the frequency can be much higher than the previous design. Of course, no volume loss and single antennas, they can reset the signal, but the problem is of course the tuning method. And to tune this cavity, we have came up with this kind of idea of the objective structure. So if we make this kind of junctions, then it's form a mechanical metamaterials. Therefore, just rotating the central cell, we can simultaneously and homogeneously expand or shrink or structure together. So basically, the frequency of this kind of photonic crystal dielectric array highly depend on the frequency of this cavity highly depend on the spacing between the dielectric pores. But thanks to this kind of design, we could simultaneously change the pore distance. And this is kind of simulations how this electric structure change the position of the dielectrics with corresponding this surface, and you can see the frequency can be tuned more than 15%, around 15% at 10 gigahertz regions. And by the way, this pi surface corresponds to conducting rods to just make the mode to be localizing inside this cylinder. And also we made this kind of prototype cavity, which can cover this frequency, cover the 10 gigahertz regions. And this is the mode map we had drawn at the 4 Kelvin physical temperature. And this red dot corresponds to the simulation result. And it's quite well follows the measurement results, but you could see there are a lot of mode mixings. This is one of the problems when we go higher frequency regions. And this video shows how it shows the intuitively how this structure can be tuned. So recently, we also have used demonstration experiment using this objective structure, but instead of using the higher order mode of the dipole mode, monopole mode, but we use the TM020 mode with this kind of configurations. So by rotating and we prepare a hexagonal objective structure like this, and by rotating the central cell, we can actually change the spacing between the outer rods, and this cyan circle actually corresponds to the dielectrics of the alumina. And by changing the distance, we can effectively change the size of the dielectric tube, which tune the frequency of the TM020. This is the mechanical structure for that, and this is the photo of those experiment. And we could cover these frequency regions, or about 5 gigahertz regions at 4 Kelvin actually. And as you could see, there in our previous design, there appears a lot of mode mixings, and one good solution has been proposed in Haystack. So also even you already very well know about that, so I just would like to talk about this. So Haystack has been proposed one of the good methods to go higher frequency regions using this kind of 7 rod conducting rods system in implementing this gear structure. But as you can see, there appears a lot of the both crossings because we are going higher frequencies. And the solution to avoid this problem is actually proposing Berkeley group is implementing this kind of photonic band gap structure, which is the array of conducting rod for the cavity wall. Then all the T mode can just go out of this defect, but only TM mode can be combined inside. So we can remove all the crossings of the T modes using this structure. And they recently published their result in this archive preprint, and these results are based on this preprint, basically, so they made this photonic band gap structure like this. And the above mode map is the case when we just use a cylindrical cavity for the outer wall. But once we replace it with this kind of photonic band gap structure, then as you can see, the mode structure becomes much clearer. So I think this is very clever way to go high frequencies, because the mode mixing is always very big problem in high frequency regions. And so far I have introduced about the XGDP and HASTEX, and now I will go to kind of summary of other groups approaches to high mass regions. So one famous group is of course ADMX, and they propose to use 18 multiple cavity array with the name of the EF5 standard frequency range. So this is a multiple cavity system, and they are considering the 18 independent electronics to take the data, and after that, considering dividing the powers digitally. So this is their proposed experimental setup, and all of these informations are based on this Patas, the presentation at the Patas workshop, and they show that they have been simulated the property of this cavity, and the form factor is around 0.5 to 0.6, and they also considering using a different cavity lengths for between these 18 cavities. Then the mode mixing regions can be slightly different for each cavity, so the experiment can be conducted continuously over all frequency regions, avoiding the mode mixing problems. And this is kind of their projections after 2 to 4 years. This design is focusing on the 2 to 4 GHz regions. And also ADMX has another group named Vera, which is also considering another way to, go much higher frequency regions. Maybe the name is volume efficient resonator actions. So their key idea is instead of using this kind of smaller size of the cavity, they consider to use this wall as a thin wall as a cavity. Then, and we want to go higher frequency regions. Instead of making whole structure smaller, we can just make the thin smaller. Then we lose only a single direction of the length scale, while the azimuthal direction and the longitudinal direction remain the same. So the volume can be maintained compared to this three-dimensional shrink. So based on this idea, they proposed using this kind of thinner cavity design. So basically there is some wedge is introduced with a certain slope, and then the field will be formed in these thin walls. And by changing the position, the height of this wedge, one can change the effective thickness between this wedge and the outer wall. Therefore, the frequency can be tuned. But you could ask the radiation loss, and their solution is introducing this kind of gradation both at the top and bottoms, which can localize the mode of this cavity into the central region. Therefore, they can minimize the loss of the radiations using this kind of setup. So this is their projections using this design. And also recently they considered implementing the combination of this thinner system and reclaim the multiple cavity system. And with this combination, they propose this kind of new idea. They call it as a beehive cavity. So basically the single one has this is a thin wall, but they introduce multiple cavity that are connected, spatially connected actually. So it is not basically multiple cavity, but more like a plasma alpha cavity or large disk cavity, I think. Yeah, but anyway, and the resonant frequency can be determined by the spacing between these wires, and also the changing the position of this central rod, conducting rod, horizontally or into the single direction. The resonant frequency can be tuned. And they also have shown that the characteristics of this cavity design actually does not change. Even when increase the number of cells or something like that, which means it can be very effectively search the high mass regions. And this is kind of their projections for this design. And also there is one other group in Italia named Fox, and they also considering using a higher order mode, using a higher dielectric cylinder that I have been explained previously. So, but their focus was not maintaining the form factor, but increasing the curve factor by properly positioning this higher cylindrical shells. So they can then localize all the electric field inside these inner regions, and therefore the curve factor can be boosted a lot, and they could see the curve factor can be more than 10 to the 6, which is a very impressive result. But the tuning is, of course, the problem for this design. And their idea is that they propose to use some clamshell design at the one side of the this wall, and this clamshell actually open the this cylindrical cavity like this, and this opening eventually change the radius of the effective radius of this cylindrical cavity, and therefore they could tune the resonant frequency even if it is small. Yeah, they propose this kind of idea for this tuning of this cavity, and also recently they have been proposed a very interesting idea as well. Named polygon facial cavity. The basic idea is they proposed using a two polygon shaped conductor and using the mode between these polygons, which is basically the same idea as a thin wall. But because this polygon already break the azimuthal symmetry, just rotating this inner polygon can change the field distribution of the this inside this thin wall. Therefore, one can change the resonant frequency, something like this. And I think this is also a very interesting idea to go high frequency regions. So now let me move on to the kind of main topic, maybe, so plasma haloscope. So as I explained before, under the magnetic field and the dark matter axion can use the breaking current density. And actually, this current density can make another resonance at the plasma frequency. However, usually the plasma frequency with like a metal has a very high frequency regions, located at very high frequency region, like more than 10 to the 15 hertz. But the frequency that we are interested in is actually order of the gigahertz. So the problem is how can lower this plasma frequency down to the gigahertz regions. And the idea has been proposed by this PRL paper. So the key idea is that by implementing the array of the wire, metallic wire, actually can limit a medium of the reduced plasma frequency for the metals, and therefore we can use the plasmonic resonance for the axion conversion into the photons. But basically, if we make this kind of geometry, this can be also considered as another type of the haloscope, of course, because if we calculate the Maxwell's equation for this kind of geometry, then it gives another TM mode that is strongly coupled to our dark matter actions. So if we calculate the electric field strength based on these two geometry, one is just a cylindrical cavity and the other is an array of the conducting wire. Then for the cylindrical cavity, it just gives trivial Bessel functions and giving the form factor of about 0.7. But with this kind of array of the metallic wire, it gives a quite complicated electric field distribution, but form factor is close to almost 1. But the most important feature of this design is that cavity frequency becomes kind of independent of the size of the cavity. And for example, if we have a wire spacing of about around 1 centimeter, then the target frequency can be go up to about 10 gigahertz. And this alpha is the Center for Axion longitudinal plasma haloscope is a global collaboration to conduct this plasma haloscope, and Yale University is one of the key collaborations for this experiment, and Stockholm University, where I'm currently in, is also one of the institute working for this experiment. Here, this is our target sensitivity using this plasmonic resonating cavity about around 10 to 20 gigahertz returns with the KSB and with the sensitivities. And I know we had a first collaboration meeting recently, but at the time I wasn't there, so I hope I can join the next collaboration meeting soon. Yeah. So let me now move on to the first last topic because of the time about the future plans of the Stockholm University. So basically, Stockholm University is also as one of the collaboration institutes for the alpha. We want to this is research work for this alpha experiment, of course. And here, this shows the group member for our Stockholm University groups. There are three senior scientists, Yang Conrad, Jan Gutzman, and me, Ezra. And two postdocs are currently working for Andrea, working for the analysis of the alpha, and Gagandi is also working for the KP design. And we are currently looking for two more postdocs for this alpha project, and we will advertise it soon. So if you are interested in it, please contact me. And yeah, and also we are going to have one more PhD soon for this alpha project. And the Stockholm, our group is located in one of the campuses, Stockholm University, named Albanoma. This is a kind of Google picture at Google Maps. The building looks like this circular arc shape. And I received one laboratory space at Stockholm University. Looks very cool, and this currently is empty. But I would like to fill those rooms with the DR and the microwave instruments for the research. The room looks like this. And yeah, of course, our objective is maximizing the scaling rate. And already, Yale University has planned to have a very strong and large magnet. So the other parameters we are focusing on, and we want to focus on the other parameters, pi factor, maintaining form factor even for high frequencies, and while tuning the frequencies, with temperature as well. So for the clever designs of the cavity and the tunings of this wire metamaterials, we at Stockholm University Group, we have proposed this kind of very interesting idea named sail design. So having this kind of asymmetric rectangular sail and rotating this sail, so this can change the electric field. Like this can effectively tune the resonant frequency of over 20%. And this is a prototype cavity, and you could see some details this paper. And this work has been done by these two, the brilliant postdoc and the PhD students. And also, I want to do some work for to lowering the system to its temperature as well. You know, we are doing the GPAs, but also I want to test the single photon detection setup as well. So we are in the process of procuring the divergent refrigerator at the Stockholm University, and maybe one of this is just some example of the barometer type photon detector setup using some SNS kitting. And also I'm considering the microwave interferometry to reach down to the standard quantum limit, even using a bad barometer. So I think many of you may not really know about this setup, so I will briefly explain what this interferometry is. So basically, the setup is something like this. So the other setups are exactly the same as a usual cake telescope, but I propose to replace the linear amplification chain to barometer type photodetector, and we can inject additional probe into the cavity. Then this barometer will read both probe and the signals. And the key thing is that we actually know the coherence time of the signal, which is determined by the Fourier vector of the axion. And if the cavity Fourier vector is larger than the axion Fourier vector, then it will be determined by the cavity Fourier vector. Anyway, the thing is we know the signal's coherence time. So every signal's coherence time, we can measure the power, and its power actually, because every coherence time, the relative phase changes. So the amount of the interference between this probe and the signal actually changes. So therefore, the variance of the power that leads to this barometer changes. So if we do some math to calculate how much variance will be at this photodetector setup or this kind of setup, then it is a summation of this things here and corresponds to the, I think, here, this major size. So this n corresponds to the number of photons. Here, the thermal noise photon, the count photon of the photodetector, the number of the signal photon, and the probe photon. And the key thing is that there appears additional interference term. It's the first term is the interference between the probe photon and the signal photon, and the last term is the interference between the probe photon and the thermal. Here, I ignore the interference between signal and thermal photon, but these two can be very small. And if we cool this whole system down to a sufficiently low temperature, much lower than the quantum limit temperature, then of course this number of thermal noise photon can be much lower than 1, because in this parameter detection setup, we can avoid the 0-point fluctuations. So this number of thermal photon can be much less than 1. And we can then calculate the signal to noise ratio for this variance operator, and it gives this kind of formula, which looks quite complicated, but I will show some class. So here I just changed the rotation from number of photon to the photon rate by just multiplying the sampling rate. Then the equation can be just reformulated in this form. And this plot shows basically the everything. So the chiral represents the signal to noise ratio of this variance for this variance operator in the logarithmic scales, and the y-axis is the amount of the dark photon rate, and the x-axis is the amount of the probe photon rate. And this plot is drawn for assuming the 1 GHz action, and corresponding sampling rate is 1 kHz, because we know pi factor of the action is 10 to the 6. And then we can divide this plot into the 4 regions based on this sampling rate, 1 kHz and 1 kHz here. And for the region 1, which corresponds to the dark count rate is less than sampling rate, then actually this already gives the best signal to noise ratio, because the dark count rate is below the sampling rate, which means each single iteration, the number of photons is less than 1. So it is already single photon detection. So you don't have to do any complicated structure. So just taking data gives the best signal to noise ratio. But in usual case, the bolometer has a higher dark count rate than the sampling rate, especially in microwave regions. So in that case, the point is that if we inject a sufficient amount of the probe photon, then we can always make this signal to noise ratio near the standard quantum limit case, making this kind of form. So even the key idea for this design is that even we have a kind of bad bolometers, using this kind of measurement protocol, because we know the coherence time of the dark matter action signal, we can always go to the near the standard quantum limit noise with any bad bolometers, once the bolometer's noise is independent of the injecting probe photons. So this is the basic idea of this variance method. And I would like to test this kind of concept in microwave regions for action searches. And the last thing is also we would like to contribute to the high quality vector cavity using the Stockholm setup. So at CAPP, I also have seen the development of the Superconducting cavity there. So we have used HTS tape, high temperature Superconducting tapes, and we put these tapes onto the surface of the cavity like this, and could achieve more than 10 to the 6 quality vector even under the strong bound field. So the basic idea is that this plasma haloscope has a lot of metallic parts inside. So we have a kind of limited quality vector due to insertion of the many conducting parts. So I know there are a lot of consideration of using the superconducting cost for the plasma haloscope, and these are kind of materials can be chosen based on IBMs. But the thing we have to consider is actually the deepening frequency, because we are applying strong magnetic field to these cavities. And once the deepening, what deepening frequency means is actually once we apply the strong magnetic field inside the superconductor, then inside superconductor there appears some vortex, and if the resonance frequency of resonance frequency of this cavity is lower than certain frequency, then this vortex can be just pinned by the wide field, so it does not introduce much losses. But once the frequency goes above this deepening frequency, then this vortex can be freely moved and makes a lot of noise, so that we lose some benefit for the superconductivities. However, ion time could be one good option because it has a very high deepening frequency, but basically this deepening frequency decreases as we increase the magnetic field, and this melting field is which is less than critical magnetic field, so we don't know whether this ion time could maintain such high deepening frequency or not. So the thing I'd like to also test is the using the LEPCO tapes, which is the rare earth BCO materials on type of the superconducting tapes, and which can have a very wide deepening frequency depending on the materials and also depending on the manufacturers. So we also get to test this superconducting tapes concept can be implemented into the alpha cavity design. So yeah, this is kind of all for my presentation. So I also have prepared several more search methods for HMS reasons, including DC antenna haloscope and also direct haloscope. But I know that I expected that I had no time to cover this, so I made this hyperlink actually. This poster, which me to summarize, yes. So let me summarize my talk. So yeah, we know action is very good and very motivated particle, and time section is especially important, and numerous volume efficient way for telescope has been proposed, including alpha. And Stockholm University, we are going to develop a resonator design, and also I'm very interested in photo detection and also superconducting cages. Thank you very much.
Thank you so much for the talk. That was really cool. Yeah, so I know for Haystack, and I might have asked this question to Mike before, but I didn't understand. So I know that we usually try to keep the form factor of our cavity about the same as we moved from our current cavity to the 7-rod cavity. And then I also think most telescope experiments use a similar form factor to us, but then seeing the Quacks cavity, it's the longest cavity I've ever seen in my life. And I was wondering, like, why do most experiments try to keep the same form factor? What effect does the form factor have on the experiment, and why is Quacks making such a long cavity?
Yeah, so basically, the reason to maintain the form factor is actually maintain the power. So of course, I mean, if we lose the form factor, then we lose the expected conversion power proportionally, and also scaling rate is proportional to the scale of the form factor. So actually, the maintained form factor is very important when we design a new kind of cavities. And for the case of Fox, actually, I'm not pretty sure why they want to make such a long cavity, but the thing I expect is that their target tunable range is not that much, less than 1% using this clamshell opening design. So for such narrow band searches, they would not much suffer from the mode mixing problem, so they could have a longer cavity, I think.
So a different form factor can decrease your scan rate even if it has the same volume. Like, so if you make it so it's like a different scaling than with the volume.
I see. Yeah, I understand your point. So basically, there is some optimal height for the cavity because the magnetic field is not uniform over the longitudinal direction because we have a limited height of the solenoid. And usually the optimal height for the cavity is around the same height of the solenoid height. Mm-hmm. So if the if the solenoid itself is long enough, then we can of course have a long cavity, but then we will suffer from many mode mixing problems. Mm-hmm. And if we have a shorter magnet, then we could have a shorter cavities.
Okay, thank you.
Yeah, thank you.
For the slide you had about the interferometry where you have like the four quadrants. So do you have a sense like on the x-axis there in terms of like you're increasing the pump power essentially, where you for like a practical device where you hit the saturation power of the bolometer? Like I'm just thinking about the sort of TS bolometers and reducing the intrinsic count of the bolometer comes at a cost of reducing the saturation power typically.
Yeah.
So there's like it goes in the opposite direction.
Yes, yeah, that's very good point. Actually, yeah, I agree that injecting more photons would make some more complicated and some challenges for the photon detectors. But let's say for the TES, we could lower the physical temperature lower than the transition temperature at first, and by injecting the photon by hitting, and then it hit the TES up to the desired temperature, and then we could see the variance at that point, I think. But it has not been experimentally demonstrated in the microwave regions, so I couldn't be sure about the practical challenges now.
Oh, I was going to ask the exact same thing to math.
Good question. Maybe can you tie in some of the questions that's been asked to the higher order cavity search that you talked about?
So can I?
The higher order mode that you were.
So give more some description about.
Yeah.
That's right. So maybe. This one or the previous one?
Yes.
Previous one. Yeah, okay. So basically, the idea is if we split this single magnetic tube into these two layer with the segmented dielectrics, it's like that, and these two each of these dielectrics actually have a same dielectric constant, but by rotating the inner layer, as you can see, effectively actually changes the thickness of this overall tube. So we could at first notice that the resonance frequency of this cavity has some high dependence on the thickness of the dielectrics, even we lose some form factors. So we came up with, we were thinking about how to change this effect. And the one idea was that implementing this kind of segmented layer, and by rotating this, this is the relative distributions. So I think it's very difficult to see, but yeah, for this, it kind of forming effectively thick dielectric tube. But once it goes to the brightness imaging, then it has a thinner dielectric layer and dielectric tube. So the resonance frequency can be tuned. The tunable range is actually not for this design. So it has been tuned around 300 megahertz at 7 years, which corresponds to around 5%. Yeah, around 5 to 6%. So one the problem is the tuning less tuning range, and also you could see some of critical mode mixings there. So we didn't run the convection experiments using this design yet.
Okay. And when you say modest form factor.
It's modest form factor is the form factor is around 0.4.
Oh.
Yeah, it's not bad.
What is the Q?
Q factor. So it highly depends on this this alumina. And I forgot the exact number, but it has a relatively high quality factor. But the order I remember is 10 to the 5. But I'm sorry, I don't remember the exact number.
Just the four phases of the noise. Would you mind to that slide? Just like there's a phase diagram of noise. There's like sampling rate times the compass signal rate times.
Yes. go to the slide. So
Yeah, so I was kind of like wondering, so why that in phase two is kind of like the signal photon rate get increased while the signal to noise actually become worse. So what's actually the source of noise in this?
So when we go to the reason 1 to reason 2 again.
Yeah, or
So yeah, so basically we cannot tune the y-axis. Actually, it is kind of given by the detector itself. But the thing is that whether our detector is located in the below the sampling rate or above the sampling rate. Okay, so this is the count rate of the detector. Yeah, so if the detector has a larger count rate, then by using this kind of measurement protocol, we can go to the near standard quantum gate.
okay,
Yes.
so this the dark count rate in y-axis.
Yes, dark count rate.
I think you can tune that, like, I guess this is the point I was saying, like, you can kind of tune that y-axis. So if you drop the saturation power, then the phonon noise through the thermal link of your bolometer
Yeah,
will
yeah.
drop.
Yeah.
So there's kind of some slice, I guess, along
Yeah,
this
yeah.
space that's like realistic bolometer design.
Yeah, I agree. Yeah.
Thank you for your talk. So I want to ask you a question that I sort of posed at the end of the alpha meeting yesterday. So in the slide where you described the dielectric wheel that you can use to tune the frequency, I guess my question is it really about the effective thickness of that dielectric? Or is it the fact that the index of refraction, this is a position dependent quantity. So I would think that if you have some dielectric with some index in a cavity, it doesn't matter like if the thickness of this thing is changing, so long as you're changing the sort of R, the position coordinate, in the function that is index of refraction as a function of R. You know what I mean? So like as someone who designs very fancy cavities and you put things in them and try to tune them, shouldn't it be the case that you can tune a frequency of a cavity just by changing sort of how the dielectric is distributed inside of the cavity, regardless of doubling thicknesses or anything like that?
So basically, the tuning the resonance mode of the cavity using dielectric highly depends on the mode we are targeting. So if we change its position with the similar order of the wavelengths for that cavity mode, then there's a frequency, of course, to be tuned. But there is a lot of factor to be considered for like a boundary condition. So we are usually interested in the TM mode because we want to place this cavity into the solenoid magnet. So in the case of electric field is all continuous over these cross sections. And by changing the position of the dielectric, of course, we can tune the resonant frequency of it. But the key idea to design this resonator is how to effectively tune the frequency while maintaining the form factor. Yeah, so I'm not sure whether I fully understood your question.
Yeah, I think you've answered my question. You know, I think in asking the question today the way I did and the way I proposed it yesterday, I was not thinking about the importance of maintaining the form factor. Just that if you move a dielectric in a cavity, you have to change the frequency.
Yes, yeah, exactly, yeah.
Yeah, you can't get around that, but okay.
Yeah.
Thank you.
In this picture, does the like, I guess the first two positions look like maybe their form factors roughly equal,
Yes, yeah.
but then the third one, is it worse or it's better?
It depends on the design itself. For this cavity, I remember it's steady, but becomes better for the other. Yeah.